Hello, my name is Martin Pike, and welcome to this lecture from the Ada Core University course on Mixed Language Programming with Ada and Java. Together we shall complete a series of slides, and then you will be assessed on your learning using some quiz questions. This lecture focuses on a specific toolset called the Ada Java Interfacing Suite, or the AJIS for short. It is a collection of add-on tools based on the AJIS library from GNAT, oriented towards integrating native Ada code with Java applications that run on a Java virtual machine. This allows standards compliant mixed Ada Java language systems. The AJIS provides an Ada binding to the low-level JNI, and it does this through the automated generation of the JNI glue code. Throughout the remainder of this lecture, we shall concentrate on demonstrating the use of the Ada to Java command line tool, which is provided along with the GNAT tools. A series of code examples are available to accompany this lecture, and all tools required to build the examples are available from libre.adacore.com and java.oracle.com. We start off by looking at a simple Ada package specification called printer, which exports a subprogram called print that accepts an Ada string as a parameter. The implementation of the print subprogram uses ada.text.io to display the string on the console. We will now continue on to showing how this Ada native code can be called by a Java main program. The Ada to Java command line tool forms the backbone of the GNAT Ada Java interfacing suite. It takes a number of options to enable detailed configuration of its inputs and outputs, and it will certainly help to examine each one in turn. The first option is the file name of the Ada package specification that we wish to produce a Java binding from. In this case, we will use our example file name printer.ads. Next, we can control the base name used by the Java packages using the -b option. It is possible to control the location of the binding output, and in this case we use the -o option to place the Ada portion of the binding in a subdirectory called Ada, and similarly for the Java part of the binding using the -c option. Finally, we identify the name of the library that needs to be loaded by the JVM at runtime to ensure all of the JNI operations are available. Ada to Java always creates a subdirectory of the same name and then uses whichever directory names were specified for the -o and -c command line options. Here we see for this example they were called Ada and Java. Underneath the Ada subdirectory we will find the files necessary to build the dynamically loadable library of native Ada code, which will be loaded by the Java virtual machine at runtime. The Ada code is all built under the JNI_binding package hierarchy and is eventually linked into a DLL with the name as specified by the -l command line option. The building is performed using the printer.gpr file. The Java subdirectory immediately contains a subdirectory with the name specified by the -b command line option. Here it is the name printer. Beneath this directory there are 4 further subdirectories for this particular example. There are the standard classes that provide the Ada string class. There is code to support Ada exceptions, followed by some library loading utility classes in the Ada to Java subdirectory, and finally there is the binding to our actual Ada code for the printer package. This particular hierarchy is specific to our example printer package, and your results and names may differ. We can now demonstrate the use of the generated binding to our native Ada code in order to use our printer code. In time-honored tradition, we shall use it to display the string Hello World. Here we have a Java main program that imports the required packages and then makes use of the print operation from the printer underscore package that has been generated by Ada to Java. Of note is the use of the Ada string Java class that represents the Ada string specified as the parameter of the print subprogram in the original Ada package specification. To complete this example, we need to build the Java main program and run it. Here is an example script that builds and runs all the code for this example. We start off with calling Ada to Java using the appropriate command line options to generate the binding. The Ada native code is then built using the GNAT GPR build tool, and once the necessary class path and path environment variables are declared, the Java compiler is used to compile our Java main program. Finally, the Java virtual machine is executed on the main program, ensuring the hello world string is output to the console. Like with any automated code generation, there may be code where the generator tool needs help in order to get the desired output. Luckily, the Ada programming language has the concept of a pragma, and any tool reading the source code has the option to use the pragma or ignore it. The Ada to Java tool happens to pay specific attention to pragma annotate statements naming AJIS identifiers that can appear throughout your Ada code. You can find the list of annotation names in the AJIS.annotations package found in the GNAT AJIS distribution. They add enough flexibility to deal with most of the intricacies when interfacing a native language like Ada and a non-native language like Java. We will encounter certain annotation names as we look at the more advanced topics of integrating Ada and Java. In particular, we will see how the annotation renaming and renaming identifiers are used to help deal with name clashes between Ada and Java source code. Before tackling some of the more advanced topics of this subject, it certainly helps to understand the basics of how types are handled between Ada and Java, as this is fundamental to understanding how to use the generated bindings. We have already encountered an example of this with the Ada string Java class within the use of our printer Ada package, and will expand on this over the coming slides. It is of course critical that the scalar types, including integers, enumerations, and real numbers, are consistently mapped between Ada and Java. And while we won't look at each specifically, we will see them used in a more general sense as global variables, subprogram parameters, and constants throughout the following examples. Composite array types are cleverly mapped by the generated Ada to Java code to proxy classes that provide subprograms that mimic the way Ada works with arrays, including providing support for indexing and a number of useful attributes. Whenever Ada to Java finds an instance of the string Ada type, it will generate a class called Ada string. Here we can see an Ada package that provides a simple subprogram that returns a fixed length string. Below we see an example of some of the more interesting operations that have been added to the generated Ada string class. getElementAt and setElementAt allow elements of the underlying character array to be both read and written. First, last, and length mimic the Ada attributes of the same name. There is a constructor for the Ada string class that passes in a Java string, conveniently allowing Ada string objects to be created from Java strings. Finally, there is a utility operation called toString, which allows the Ada string object to return a Java string version of itself. It is possible for Java code to use global variables and constants declared in the publicly visible part of an Ada package. Ada to Java will use specific mappings for any scalar types, and then provide read and write operations for variables, and read operations for constants. Here are two examples of this by way of a Java main program that will output the values of the global variable and constant to the console. First, we have an initialized package level variable called myGlobal, for which two operations are generated in the globvar_package Java package. These can be used to read and write myGlobal. Similarly, there is a single operation for myConstant that only permits the value to be read as it was declared constant in the Ada code. This Java main program, when compiled and executed, we will see the output of the values 40, 60 and 50 respectively. An Ada array type is mapped by Ada to Java into a proxy class with a name that matches the type name. Given the Ada package called Ada array shown here, along with the appropriate invocation of Ada to Java, the an_array Java class will be generated. It contains a constructor that allows Java objects to be allocated, and operations that provide similar capabilities to how Ada native code would access objects of the array type. It is not surprising to see that the operations are similar to those available for the Ada string class, seeing as strings are arrays of characters. The records type Ada package defines two record types, one of which has been used to type a field within the other. The nested record field of a record type is therefore a nested record data structure. Passing this Ada package specification through Ada to Java results in a Java proxy class being generated to model the nested record type record, along with setter and getter style operations for each of its fields. Ada to Java has also generated a Java proxy class for the A record type along with the necessary setter and getter operations for all the fields including the nested record data structure. This example demonstrates that simple composite data structures like records can be used in both Ada and Java, enabling existing algorithms based around non-object oriented data to be reused in a pure object-only environment like Java. It is possible to effectively use Ada type extension in Java through Ada to Java support for tag types. Here we have a tag type with a primitive subprogram called printme, which accepts a string parameter to be displayed. We then have a second type derived from the first, which has an overridden primitive subprogram for printme, again accepting a string parameter to be displayed. Finally, we have a package level procedure called callPrintMe, which can accept an object val at any point in the type hierarchy we have built up. Here is a UML diagram to show the type hierarchy using the class notation, including the operation names. Here are the implementations of each of the subprograms. Each implementation of printme outputs a string specific to its associated type. Note that the call in the Ada callPrintMe is dispatching, so at runtime the correct implementation of printme will be called based upon the tag of the val parameter. Here is an initial version of a Java main program that instantiates objects using types defined in Ada with Java versions generated by Ada to Java. If we were to build and execute this Java main program, then the output would be as follows. It is also possible for Java classes to continue the type extension from any Ada tag type. So here we've extended a tag type to give a Java child and overridden the printme subprogram. Given a slightly different main program, we get the following output. You can see the callPrintMe subprogram successfully dispatched across the Ada and Java language boundary. Access types, and indeed pointers, are not normally something languages like Java or C# have to ordinarily contend with. It is possible, however, you will be putting together a binding to an existing piece of Ada code that employs access types. there needs to be a way to ensure the AJIS subprograms can retain their interface specification when called at runtime, even if the ADA is expecting an access type. An example code here shows a record type along with an associated access type with a primitive subprogram. The implementation of the primitive subprogram displays the value of the field within the record targeted by the access type parameter called obj. Assuming we have ran this ADA package specification through ADA to Java, the necessary code will have been generated to allow the following Java main program to compile. We've instantiated an object of our target type, modified its field value, and then passed it to the use access type ADA subprogram. Notice the object is passed in exactly the same way as if it had been a non-access type object. ADA to Java has taken care of ensuring the ADA subprogram receives the parameter argument correctly. But in fact this code will fail to run, with a runtime exception being raised and a message that indicates the value of obj cannot be escaped. We can encounter a scenario where an object is passed by reference from Java to ADA, where the reference is stored globally by ADA, only to end up with the referenced object becoming inaccessible due to the Java garbage collection and finalization of the ADA proxy. This is a classic case of a dangling reference, and ADA to Java takes a simple approach to dealing with it. When the Java side is responsible for pointer memory management, then an exception will be thrown in Java on an attempt to pass a reference to a native object as an actual parameter, when the formal is of a named or anonymous access type. This is what has happened here. There may be situations where this is harmless, and so ADA to Java supports the assume escaped identifier for pragma annotate. This will ensure the exception is not raised and shifts the responsibility onto the programmer to ensure the dangling references cannot occur. During development, it may be sensible to not use the assume escaped identifier to catch any dangling references. With this in mind, the ADA to Java tool can globally apply this identifier by using the following command line option. This will either enable or disable checks for the object ownership. If we regenerate our binding with the pragma annotate applied, we get the following output when our Java main program is executed. It's time to look at a more advanced use of access types that allow ADA subprograms to call Java operations. Support for ADA calling Java operations is provided by access types to subprograms using a callback pattern. Here we see a package called jprinter, which provides an operation called call_back that accepts an access to subprogram parameter and a string parameter. The access to subprogram type targets a procedure that accepts a string parameter. Notice the application of the pragma annotate to the meth access to subprogram parameter. This must be applied, otherwise the object coming from Java will be considered non-escapable and an exception will be raised at runtime. The implementation of the callback subroutine is fairly simple. It passes the string parameter as an argument to the access to subprogram's target. The key here is that ADA to Java is going to generate a code infrastructure that allows Java operations to be passed to the ADA code as the target of the access to subprogram type. It does this by creating an abstract Java class with an abstract operation that will be called by the Java binding to our callback ADA subprogram. Here we have extended the printCB class and implemented the abstract printCB body operation. The implementation converts the string parameter from an ADA string to a Java string and displays it on the console. This essentially allows us to implement our Hello World example using a Java main program calling an ADA subprogram which in turn calls a Java callback class's operation. Here is the Java main program creating an instance of the callback class that is passed to the callback AJIS subprogram along with a hello world AJIS string. If we were to build and run this program, we would get the string hello world output to the console. When operators are overloaded in Ada, the corresponding Java name is set by the binding generator to one of the entries in the following table. An example of this is provided in the code snippets on the right of this slide, with an Ada package specification which includes operator overloading. First, there is an Ada package specification containing an operator rename of the plus and greater than or equals operations for the example _C type. The resulting Java class that represents the op_overload package is shown below, and you can see the appropriate Java names from the table have been used to identify the operator methods. A Java main program can then use these operator overloaded methods as shown in the third code snippet, along with the associated output from when this code is built and executed. If you encounter Ada package specifications that have overloaded operators, then be prepared to see and use these method names from your Java code. If Ada subprograms from the same package specification produce the same Java profile for operations, the binding generator will detect the problem and generate only the first entity. Other entities of similar names will be ignored with a warning. Here we see an example where this would occur. While an Ada compiler is happy to deal with this name clash, the Ada to Java code generator must be given some help when it encounters this style of code. If we were to run Ada to Java against this Ada package specification, we would be met with the following warning. To prevent this, you can use the rename identifier from the AJIS.annotations package along with the pragma annotate statement to define the Java name corresponding to an Ada entity. This then allows us to use the two functions f from a Java main program as follows, but the Java code must reference them using their renamed identifiers, in this case f_i1 and f_i2. This program, if built alongside the Ada package body shown here, would result in the output at the bottom of the slide. It is possible for Java operations to handle exceptions raised by native Ada code that they have called. There is an example of this in the package specification shown here. It declares an Ada exception and then deliberately raises the exception in the body of the specified subprogram. Running to Ada to Java on this package specification yields two Java classes, one that represents the actual exception and another for the overall package. Let's look at the characteristics of the Java class that represents the exception. The class name matches the name of our exception, and it extends an AJIS class called native exception and implements the internal Ada exception interface. The key operation here is create occurrence, and this is what is called by the GNAT glue code if the exception is to be raised by the native Ada code. Given the following Java main program, we can see a try-catch block around the call to the native Ada subprogram. The catch statement has used an object E of our exception class type that we generated using Ada to Java. If this code is built and executed, then the string exception thrown from Ada is displayed on the console. We have now reached the end of the slides section of this lecture. You should now have enough knowledge of this subject to complete a small quiz with questions designed to test your understanding. Each question is marked, and you will have a chance to review your score at the end of the lecture. Good luck with the quiz. The following Java main program allocates a string and displays it on the console. Click on the tick icon if you think this code is correct, or the line of code you think is incorrect. The code is incorrect. The string used an allocated object of the AJIS class, but attempted to assign it to a Java string object. The two types are incompatible. However, the AJIS class has an operation that can return a Java string version of itself. The correct code is shown at the bottom of this slide. The ADA package specification given here defines a subprogram that can raise a constraint error exception at runtime. Any caller of this subprogram should be prepared to handle the occurrence of this exception. The subprogram implementation is shown here, and we can see there is a local exception handler that displays a message. The Java main program calls this ADA subprogram within a try-catch block. What do you think the output of this program will be at runtime? Please make your selection from the following list. The answer is both the string exception in ADA and the string exception thrown from ADA. This is due to the raise statement within the ADA exception handler that causes the exception to be propagated out to the Java caller. This question looks at how ADA arrays are accessed from Java. The ADA package shown here provides a two-dimensional array of natural numbers and a subprogram called setStrings. The implementation of the subprogram assigns a series of natural numbers to the array parameter. The Java main program creates an object of our nested array type and calls the ADA subprogram. It then uses some operations from the ADA binding to our package in order to print out a series of natural numbers. Click on the tick icon if you think this code is correct, or the line of code you think is incorrect. The code is correct. The outer array has an index from 1 to 20, and the Java code used the last operation to obtain the 20th nested array. This nested array was then iterated over using the length and getElementAt operations. Each retrieved element was then displayed on the console. The result of this program is shown here. Question 4 presents a situation involving ADA access types. Here we have a record type called target and its associated access type. A subprogram will display the value field of the access target parameter on the console. Here a Java main program creates an instance of the Java target class and provides as an argument in a call to the ADA subprogram. What do you think the output of this program will be at runtime? Please make your selection from the following list. The answer is that nothing will be output by the AJIS subprogram. The Java main program will ultimately fail to call the AJIS subprogram at runtime due to an exception being raised in the binding. In order to resolve this issue, the ADA package specification must be adjusted to include a pragma annotate, as shown in red here. This question tests your knowledge of how ADA to Java handles ADA overloaded operators. Here is an ADA package with some overloaded operators for a derived type, and a Java main program that will output the Boolean result of an expression using the ADA code. What do you think the output of this program will be at runtime? Please make your selection from the following list. The answer is the string true. Here is an alternative version that uses the ADA equality operation op_equal in place of the Java equality operator. This demonstrates how easy it is to switch between using ADA and Java versions of operations. Study the two entities declared in the following ADA package specification. Now look at the Java main program. Click on the tick icon if you think this code is correct, or the line of code you think is incorrect. The code is incorrect and will fail to compile. my_constant was declared constant in the ADA package specification, so ADA to Java would not have built the operation whose use has been attempted. Study the following piece of ADA code and insert the correct pragma Annotate identifier to ensure this code functions correctly at runtime. The answer was the assume_escaped identifier. Study the following piece of ADA code and insert the correct pragma Annotate identifier to ensure this code functions correctly at runtime. The answer was the rename identifier. This question tests your understanding of how ADA tag types can be used by Java programs. Take this ADA package specification that contains a type hierarchy and an operation. The Java main program extends this ADA type hierarchy using a class and then goes on to use an object of this class. What do you think the output of this program will be at runtime? Please make your selection from the following list. The correct answer is highlighted. Java programs can extend ADA type hierarchies and provide overriding operations. Something of note is how the default value of the Boolean field was in place at the time of the call to the Java binding runtime. The final question presents an attempt to call a Java operation from an ADA subprogram. Observe the ADA package specification and Java main program shown here. Click on the tick icon if you think this code is correct, or the line of code you think is incorrect. The code is incorrect and will fail to compile. It is not possible to simply provide a Java operation as the callback when calling the ADA subprogram that is expecting an access to subprogram typed argument. There must be a Java class that extends the class used to represent the access to subprogram type, and it must override the body subprogram. Thank you for attending this lecture from the Ada Core University. I hope you have found it a valuable step in learning the Ada programming language, and that you continue on to the other lectures in this course on mixed language programming with Ada. Thank you.